Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Aveda Inamdar, Senior College. Now, in the paper Discrete Mathematics, now we start with Unit 4, that is Recurrence Relation. Now, next is linear recurrence relations with constant coefficients. Now, first see what is the definition or what is the format of linear recurrence relation with constant coefficients. A linear recurrence relation with constant coefficients is a recurrence relation of the form C0 AR plus C1 AR minus 1 plus C2 AR minus 2 plus and so on CK AR minus K, which is equal to FR, where C0, C1, Ck are real constants with C0 and Ck non-zero. F of r is a function of r and is valid for all r greater than or equal to k, k being a positive integer. The integer k is called the order or degree of that relation 1. Now see here C0, C1, C2, Ck, all these are multiples of AR minus 1, AR minus K respectively. So AR minus 1 and so on. These are nothing but terms of that sequence for which the recurrence relation is obtained. Now C0, C1, C2, Ck and so on, all these are constant, means they are real numbers, out of which C0 and Ck are non-zero. Now what is the right side? F of r, it is a function of r. It means it may be r, r square, r plus 2, 2r plus 5 like that, or it may be constant also. So such type of recurrence relation is known as linear recurrence relation, because here all AR have power equal to 1. That's why it is linear recurrence relation and their coefficients are constants, means they are real numbers. So it is a linear recurrence relation with constant coefficients. Now the value k is called as the degree or order of the recurrence relation. For example, 5AR plus 7AR minus 1 is equal to 2 raised to r. Now see, this is one linear recurrence relation with constant coefficients. So if you compare it with this relation 1, C0 AR. So C0 AR means C0 is 5 here, plus C1 AR minus 1. So this is the term A1 AR minus 1. So its coefficient C1 equal to 7 and f of r is equal to 2 raised to r. But when the last term is ckar minus k, it has degree k. It means we are going from ar to ar minus k. Then it has degree or order k. Now here only two terms are there, ar and directly ar minus 1. So this is a linear recurrence relation of first order with constant coefficients. Similarly, 2ar minus 8ar minus 1 plus 3ar minus 2 is r square plus 4. Now here AR2 it is AR minus 2. So comparing it with AR minus K. K is 2. So this is a second order recurrence relation with constant coefficients. Here f of r is r square plus 4. Now next is characteristic equation. If C0 AR plus C1 AR minus 1 plus C2 AR minus 2 plus CK AR minus K is equal to f of r is a recurrence relation with constant coefficients of degree or order k, then an equation of the type, see how to write equation from it, C0 alpha raised to k plus C1 alpha raised to k minus 1 plus C2 alpha raised to k minus 2 plus and so on Ck alpha raised to k minus k equal to 0. That is C0 alpha raised to k plus C1 alpha raised to k minus 1 plus C2 alpha raised to k minus 2 plus and so on Ck equal to 0, where alpha is constant, is called characteristic equation of the recurrence relation. So as linear recurrence relation has degree or order k, we are getting a characteristic equation in which the maximum power of alpha is k. So the constant C0, C1, Ck remain same. Instead of AR minus 1, AR minus k, we are replacing them by alpha to the power k, then k minus 1 and so on. Now roots of characteristic equation of the recurrence relation are called characteristic roots of the recurrence relation. So once you solve that characteristic equation, then we get the values of alpha, which are nothing but roots or characteristic roots of that recurrence relation. Now we will see how to solve homogeneous recurrence relation. Now first see the definition. A linear homogeneous recurrence relation is a relation of the form C naught AR plus C1 AR minus 1 plus and so on Ck AR minus K is 0, where C naught, C1, Ck are real constants with C naught and Ck non-zero. So in general, the linear recurrence relation with constant coefficients has formed C naught AR plus C1 AR minus 1 plus Ck AR minus K equal to f of r, where right side f of r is a function of r. But when right side is 0, then in that case, that linear recurrence relation is known as homogeneous recurrence relation. Now, what is homogeneous solution? A solution which satisfies this linear homogeneous recurrence relation is called a homogeneous solution. Now, steps for solving linear homogeneous recurrence relation of order K. Now see the first step. Write the characteristic equation of the equation 2, which is given as C naught alpha raised to k plus C1 alpha raised to k minus 1 plus and so on Ck equal to 0, where alpha is constant. So the first step is, for the given linear homogeneous recurrence relation, we write its characteristic equation in terms of alpha. Second, find all roots of the characteristic equation. These roots are called characteristic roots. So we solve that equation 3 and we find its roots. Then third, now there are two types of roots. See, roots may be distinct or some of them may be repeated. So depending on the nature of roots, we have to write the solution. See, we get different cases as follows. Now the first case, the roots alpha 1, alpha 2, alpha k of this equation 3 are real and distinct, means no two of them are equal. Then the homogeneous solution of second, means given recurrence relation, is as ARH, H for homogeneous solution, is a1 into alpha 1 raised to r plus a2 into alpha 2 raised to r plus and so on ak into alpha k raised to r, where a1, a2, ak are constants to be determined by the initial conditions. So as there are k roots alpha 1, alpha 2, alpha k, there will be k constants a1 and 2, ak in that homogeneous solution. But we can write this solution if alpha 1, alpha 2, alpha k, all these roots are different and real. Now second case. Suppose that some of the roots of the characteristic equation are repeated. Let alpha 1 be a root of multiplicity m. Multiplicity m means alpha 1 is repeated m times. So only alpha 1 has multiplicity m, means it is a repeated root m times, and the remaining roots are distinct. Then in that case, how to write the homogeneous solution? So as alpha 1 is repeated m times, we write a1 r raised to m minus 1 plus a2 r raised to m minus 2 and so on am bracket multiplied by alpha 1 raised to r plus, for remaining alpha 2, alpha 3, alpha k, we get b2 alpha 2 raised to r plus and so on bk alpha k raised to r, where a1, a2, am, b2, 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 b3, bk are constants to be determined by the initial conditions. So depending on the nature of roots, we have to write the solution. Now first example, write general form of the solution of a linear homogeneous recurrence relation with constant coefficients if its characteristic equation has roots 2, 3, 5. Now here see the nature of roots. The roots are 2, 3, 5, all are distinct, and hence as there are 3 roots, it means we need 3 constants, say a1, a2, a3. Hence the solution is AR equal to ARH is a1 alpha 1 raised to r plus a2 alpha 2 raised to r plus a3 alpha 3 raised to r, where alpha 1, alpha 2, alpha 3 are roots, namely 2, 3, 5 in this case. So it is a1 2 raised to r plus a2 3 raised to r plus a3 5 raised to r. Now second example, write general form of the solution of a linear homogeneous recurrence relation with constant coefficients if its characteristic equation has roots -1, -1, -1, 7, 7. Now if you observe these roots, then they are not distinct. So -1 is appearing 3 times, means it has multiplicity 3, and 7 is appearing 2 times, means 7 has multiplicity 2. So when the multiplicity is m, here r raised to we start with m minus 1. So as minus 1 has multiplicity 3, for taking powers of r we start with 2, then we reduce it by 1 and then by 1 again. So r square r and r is to 0. Same way the multiplicity of 7 is 2. So for 7 we take the power of r 1 and then 0. So how to write the solution here? AR equal to ARH is equal to, in first bracket, as -1 is appearing 3 times, we need 3 constant. So A1R square plus A2R plus A3 into -1 raised to R plus another root 7 as multiplicity 2. So A4R plus A5 into 7 raised to R. Now we will see how to solve the homogeneous recurrence relation. Now see the question. Solve AR minus 7 AR minus 1 plus 10 AR minus 2 equal to 0 with A not equal to 1 and A1 is equal to 2. So these are the initial conditions. Now first see, comparing it with the linear homogeneous recurrence relation with constant coefficients, that is C naught AR plus C1 AR minus 1 plus CK AR minus K equal to f of R. So here f of R is equal to 0. So this is a homogeneous recurrence relation. And see, whenever it is C naught AR plus C1 AR minus 1 plus CK AR minus K, then its degree or order is K. Now here it is AR minus 7 AR minus 1 plus 10 AR minus 2. So degree of this recurrence relation is 2. Now we write its characteristic equation. Now as the degree of recurrence relation is 2, maximum power of alpha is 2. So we replace AR by alpha raised to 2. Now everywhere replacing r by 2 and taking it as power of alpha, we get alpha square minus 7 alpha raised to 2 minus 1 plus 10 alpha raised to 2 minus 2 is equal to 0. That is alpha square minus 7 alpha plus 10 equal to 0, which is a quadratic equation. Now we find its roots. Now find two numbers such that their product is plus 10 and their addition is minus 7. So such numbers are minus 2 minus 7. So we get alpha minus 2 into alpha minus 5 is 0. Now as the product is 0, either first term is 0 or second term is 0. So we get alpha minus 2 equal to 0 or alpha minus 5 equal to 0. So alpha equal to 2, 5. These are the characteristic roots. Now depending upon the nature of the roots, we have to write its homogeneous solution. Observe the roots. They are 2 and 5 which are distinct. And hence we write its homogeneous solution as ARH is equal to. Now as there are two roots, we have to take two constants A1 and A2. So A1 2 raised to R plus A2 into 5 raised to R. Now we decide values of A1 and A2 by using initial conditions. Now initial conditions A0 and A1 are given. So first we put R is equal to 0 in equation 1. So we get A0 is A1 into 2 raised to 0 plus A2 into 5 raised to 0. But these two values are 1. So A1 plus A2 is equal to 1, where A0 equal to 1 is given in the problem. Now we call this equation as equation number 2. Now another value is given as A1. So put R equal to 1 in equation 1, we get A1 is equal to A1 into 2 raised to 1 plus A2 into 5 raised to 1. Now A1 is given as 2. So 2 is equal to 2A1 plus 5A2. That is 2A1 plus 5A2 is equal to 2. Now we got two equations, namely 2 and 3 in terms of A1 and A2. Now we solve these simultaneous equations. But to find the values of A1 and A2, either coefficients of A1 must be same or coefficients of A2 must be same. So here it is easy to make coefficients of A1 2. by multiplying this equation by 2. So what we do? We multiply equation 2 by 2 and then we subtract it from equation number 3. So we get 2a1 plus 5a2 equal to 2 minus 2a1 plus 2a2 is equal to 2. Now a1 get cancelled. 5a2 minus 2a2 is 3a2. So 3a2 is equal to 0. Implies a2 is 0. Now equation 2 is a1 plus a2 equal to 1. So putting the value of a2 equal to 0 in that equation 2 we get a1 is equal to 1. Now our homogeneous solution of given recurrence relation is AR is equal to A1 2 raised to R plus A2 into 5 raised to R. But value of A1 is 1 and value of A2 is 0. So it is 1 into 2 raised to R plus 0 into 5 raised to R. So this is 0. So it is just 2 raised to R. Thank you. So this is the end of our unit number 4.